So let's talk about Go A 2007 paper. So it is a paper on randomized field experiment, and they conduct the experiment on bicycle messengers in Switzerland. So please read the paper for detailed experiment setup. So these bicycle messengers are free to choose how many hours to work, which is important because one potential source of bias is that most of people can only work 40 hours a week, but here in the setting, they don't have this restriction. A second important point is that these bicycle messengers, they don't have fixed wage. So their earnings are given as a fixed percentage of daily revenue. And the experiment is set up as that their wage rate, the fixed percentage, temporarily increased by 25%. And the treatment and control group were rotated after 4 weeks. Okay, so people were randomly people or bicycle messengers are randomly assigned into the treatment group and control group. In the first period, the treatment group received a 25% increase in their wage rate, and in the second period, the control group now become the treatment group and receive a 25% increase in the wage rate. And these are the average revenue and average shifts they done. So first, we can see that in the 4 weeks period before the treatment, there is no difference. Right? You can see that. There's essentially no difference. And if you do a statistical test, they are not significantly different from zero. So these are the standard errors, right? So if you, because the standard error is larger than the difference, so we know that if you conduct a t-test, you won't be able to reject the null hypothesis that the difference is 0, right? So, So why the difference is 0 or close to 0? Because we know that we conduct a randomization. If the randomization is successful, we know they should be the same on average, right? So the average revenue and average shift should be the same. And here confirms that the randomization appears to be successful. In the first period, in September 2000, we see that Group A, which received 25% higher wage, worked about $1,100 more in terms of the revenue, and work 4.15 more shifts. And you can see that the difference is actually statistically significant, because this here is roughly twice large of that. In the second period, Group B received 25% higher wage, and again we can see that the group received higher wage actually and more, and work more shifts. And actually the magnitude is quite similar, right? So Group B here, Group B here work about 3.8 more shifts, earn about 940 more. So was the randomization successful? How to check? Well, we know it's likely to be successful because the pre-treatment average seems to be the same. So if you check the statistic for the pre-treatment revenue, they are close to 0, and we won't be able to reject the null hypothesis that they are the same. How to get the treatment effect, the causal effect? If we use period 1 as an example, we can just use a simple difference. That will be our estimate of the causal effect, the effects of wage increase on labor supply, right? So the labor supply here is measured by revenue and shifts. We can also use difference in difference. Right. So if we want to conduct a difference in difference, we can use the difference in the treatment period and minus the difference in the before period, the 4 weeks before. Similarly, we can do that with the revenue, right? So this is difference in period 1 minus the difference in 4 weeks before. You can do that using period 2 as well. And in fact, if you want, you can even use period 1 and 2 to conduct a difference in difference. Basically, if you want, you can use say 4131 here minus 274. So this is the difference for group A minus the difference in group B. So you can do that instead of compare the period 1 or period 2 versus the 4 weeks period before, you could use period 1 and period 2 and construct a difference in difference. Theoretically, they are all valid or okay. They are all good estimates because we have a randomization design. And in fact, because the randomization is successful, the difference in difference estimates and the simple difference estimates should give you similar treatment effect. In fact, you can see here, because the pre-treatment period is very small, the pre-treatment difference is very small, so the difference in difference is indeed very similar to the simple difference. However, even though we get the treatment effect, we still needed to conduct statistical inference, right? We want to know whether these treatment effects are statistically significant, especially we want to test whether they are statistically significant different from 0. So the easiest way to obtain standard errors anti-statistic is to use regression analysis. So you all learned Quant 201 before, so we are going to skip the detail here. So regression analysis allows, one advantage of using regression analysis is it allows to control for other variables. For example, if you wanted to control for the temperature, because like in period 1, maybe warmer than period 2, or if you want to control for gender or something like that in your research design, you can also do that. In the context here, because we have a randomization research design, controlling for these variables is not necessary, but it can increase precision. So it's still better if you can control for these control variables. So how do they do that? Well, because the treatment and control group were rotated, so in the regression they can be combined together in one single regression. And intuitively, the treatment effects estimated from the regression is the average of treatment effects in both periods. Because here, if you do a difference in difference or a simple difference, period 1 and period 2 are slightly different. When you use regression, you pull them together, the estimates from the regression is roughly the average of the two periods. So here is the regression results. If you are interested, so this is actually the regression they run. They showed it in the paper. So TIT is a treatment dummy. That's what we are interested in. Alpha I is something we call individual fixed effect. So individual fixed effect control for anything fixed within an individual. For example, it's control for gender, it's control for preference, even though we don't observe preference. When you control for individual fixed effect, that can control for anything fixed within an individual. And that's is simply, so the individual fixed effect is simply a dummy variable or a binary variable for individual. And it's also important because effectively, when you controlling for individual fixed effect, we compare the difference within the individual. So that's actually that's the common way, the standard way of implement a difference in difference research design in a regression framework. You control for individual fixed effect. We also control for treatment period 1 and 2. That's the dummy variable for period 1 and period 2. Again, that's we control for anything fixed within the period, like temperature or just something like fixed within that period, but it's not very important. So what we really care about is, of course, the treatment dummy, and we want to. This is a treatment effect in terms of the revenue, and this is a treatment effect in terms of shifts. And you can see this is very close to what we get from the simple difference or difference in difference before, right? The regression result here essentially suggests 25% increase in wage rate result in about $1,000 increase in revenue and about an increase of roughly about 4 shifts. Okay. So how can we so what is the estimated elasticity of labor supply based on these estimates? So we know the average revenue between group is this number and this number, right? So what is the elasticity of labor supply, right? That's the percentage change in labor supply over the percentage change in wage rate. right? So we can use the estimate we get, like $1,000 revenue over 4 shifts, and calculate the percentage change in labor supply. Right, so the estimate in elasticity is actually very straightforward, right? So we know in the numerator, it's 1,000 over the sample mean, that's a percentage change. And in the denominator, that's 25%. So you can use either the period 1 or period 2 average, but it doesn't really matter. We get a elasticity about 1.1 to 1.2. Is it elastic? Yes, right? Because it is greater than 1, so suggesting that the labor supply elasticity is elastic. If we calculate the same by in terms of shift, the labor supply elasticity is even greater. It's about 1.5. It's even more elastic, right? So that's essentially, for example, if we use 11.9 period 1, so that's 4 over 11.9 and 25%, which is 1.34, right? That's how we get the number. Right, so the results suggest that labor supply may be quite elastic, unlike the previous literature suggests, right? Including the textbook, the old literature tend to find that the labor supply, especially for male, is small and inelastic. It's very close to 0. However, the experimental evidence here suggests that maybe the old literature is not right. The old literature may be biased because, for example, people won't be able to freely choose how many hours they can work. The result could be driven by individual heterogeneity. Some people prefer to work more, and we cannot control for that. Here we have a perfect randomization design, and it shows that the labor supply elasticity is probably much bigger than we previously thought. And in fact, many recent literature supports this finding. Like there's a paper by Stafer. She finds a similar elasticity among Florida lobster fishermen. So it's a similar research design. It's not a randomization, but these lobster fishermen also can freely choose their hours of work, and it appears that the labor supply is much larger. There's also a paper on like a New York taxi driver. It also suggests a much larger labor supply elasticity. Potential limitation. Can you think about some potential limitation in the Fur and Goe 2007 paper? So no research is perfect. So can you think about some potential limitations here? The first one is external validity, right? It's a very specific setting, right? So people may question, is the elasticity of bicycle messengers in Switzerland similar to the prime age working males in New Zealand or in general? So of course, I mean, this is a valid concern, but at least for the labor supply elasticity, for the labor supply case, we do find a lot of paper in different settings, like the lobster fishermen in Florida or New York taxi driver, they all appear to have a larger, quite elastic labor supply elasticity. So I would say this is a very concern, but it does not say the research is invalid. It just says we need more research in general. We needed to have a lot of research to have accumulated evidence. Right. One problem is the small sample size. There are only around 40 messengers, so there's some statistical concern that maybe we don't have enough precision. You can also try to question whether the control group is a good control group, right? So even though they have conduct a randomization, but one potential concern is that the control group could be contaminated. So the reason they rotated the control group and treatment groups is because they only have around 40 bicycle messenger. So to increase the statistical power, they needed to do that. Otherwise, they don't have enough people. They don't have enough observations. The statistical power is not enough. But to do that, there's a potential concern that the treatment group, the control group, is contaminated because they were treated in the first period, right? So, for example, the group A, they were treated in the first period and then used as a control group in the second period. So one potential concern is maybe, for example, they become stronger because they actually work more, right? So they may become physically stronger. And then you use them as a control group in the second period. That may bias the estimates. That's actually a very concern. On the other hand, we saw that the simple difference in the two periods are actually quite similar. So even if there's some small bias, it's probably not too big to be worried about. So the Fur and the Yu-Wei paper you need to read then. That's required. Let me repeat again. You don't need to read it from page 1 to the last page. Mainly just read the introduction, and if you want, you can just look at the. If you are interested, look at their experimental setting and maybe look at the table we cover and see how they discuss their findings. And the supplementary paper, you can take a look, but there's no requirement at all. Appendix. So usually during the lecture time, I don't have time to cover the appendix, but since we are doing recording, I'm going to talk about them. If you want to skip them, just skip them. They will not be covered in the test. So this is our general setting of the labor supply curve, right? So we have hours of work as a flexible function, in general a known function f, and it's a function of wage rate and non-labor income, and we can rewrite that as a wage rate and reservation wage. And in general, this is an unknown function. We don't know that it may not be linear, maybe very complicated function form. As economists, what we do, we want to use some simple known function to approximate the unknown function f. So typically we use a linear function, and that's why you see this linear function here. We use a linear function. Right, so we rewrite the function as also work as a linear function of wage rate, non-labor income. In regression, we can control for other control variable like number of children, gender, age, maybe education. Education. That anything that could affect reservation wage. Okay. Alternatively, people like to use log linear function. as an approximation for f. And the good thing about log linear function is the beta here, the beta you get can be interpreted as labor supply elasticity directly. Of course, potential problem is that if you just run a regression using typical survey data, this kind of regression tend to be biased. Right? And if you remember, like I use the survey, if I run a regression, use the data collected from you guys, I actually get a negative labor supply elasticity, even though the true labor supply curve is actually upward sloping, and the true labor supply elasticity among you guys is actually positive. But if I just run a naive regression, it will be negative. Okay. But however, I mean, here we are not going to talk about bias. Just talk about conceptually. Let's say somehow we actually have wage rate randomly assigned. What a regression is doing, because we know that the econometric framework is actually somewhat different from the economic theoretical framework. So here I try to connect them together. So we are not going to, so here we don't worry about the endogeneity issue. Here we assume the hourly wage is actually randomly assigned, so we don't need to worry about endogeneity. Okay. So what is a regression like this kind of things, this linear or log linear is doing? It actually captures the average. Okay, so it's actually capture the average labor supply curve. So how is that? So you can imagine that, let's say we have a function like this, and at wage rate 15, some people may willing to work 15 hours. Some people may willing to work 10 hours. And some people may only wish to work, say, 3 hours. And there's a distribution here. Right? So there's a distribution, so there's also average. And the average is here. And if we connect the average across each conditional distribution, we get the average labor supply curve here. And that's actually how I show the labor supply curve in previously in our classroom. Right? So that's just, I take average, and that's average labor supply curve. Okay. Then how can we use a regression to fit the average here, the average labor supply curve? So our goal as economists is we want to use a regression, like a linear regression or a log linear regression, to fit this average labor supply curve. So that's what we want to do. We want to use a linear function, for example, to approximate this unknown labor supply curve function. Or a log linear, for example. So a log is actually slightly so a log linear is like this. So it's actually have some curve, and that's why we call it. So yeah, so this is a log linear. So it's linear in log, but it has some curve.